So in the last class, we have seen the circuit F is equals to A plus B C prime. So usually it is not given, the final circuit is not given in the exam, but I gave the final circuit as F is equal to A plus B C prime. So what we are having was a truth table. So as usual, we first you draw the truth table A, B, and C. I'm drawing the truth table for the expression A plus, A, B, C. So again, you have to list all these numbers 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And what was the final output, which was F, which is the final output. So the truth table look like this. So 0 here, 0 here, and 1 here, and 0 here, and this all these are rest are 1. So this was the truth table. The final circuit I gave was F is equals to A plus B C prime. I said that I go to school on a Sunday. A means a Sunday, or on a holiday, if there is no exam tomorrow or something like that. So that's why I put A, B, C. I mean, you can give any analogy. I just follow the same analogy for this circuit, but we are not given the final expression here. So we're going to build from the truth table. So these are called as the min terms. One thing you just want to know that this is M0, M1, M2, M3, M4. I have to check the definition of min terms, but these are called as the min terms. But we are collecting the min terms for which the output is 1, right? So this was 1, this is 1, and for this is 1, and for this is 1, and this is 1. So these are called as the min terms, and we are seeing only the output for, we are so collecting only the min terms for which the output is 1. And this is how we wrote the final expression to rewind. So I wrote, so M, this is 1, right? So A is 0, B is 1, and C is 0. So I will write as A prime, sorry, A bar, B, and so I'm not using prime, I'm using bar. So A, B, C bar, right? This is 0, 1, 0. And plus for M4, the min term M4, the output is 1. So I will write as A, B prime, sorry, B bar and C bar. And here 1, 0, 1, I will write as A, B bar, C bar, the output is 1. And here M6, for which the output is 1. So this is going to be A, B and C bar. And finally, we have all ones for which the output is 1, right? A, B, C are all ones, so output is 1. So do you have any questions of how I write this expression? This is the expression that one of the, the assignments will be doing this often. Any questions on this, how I wrote this final expression? Anyone? Go ahead. Do you have a question? F is a function, it's output. It's just, we call it, a function, right? In mathematics, so see, like in quadratic form, like f of x is equal to x cubed plus x squared plus 1, or this is not quadratic, but this is a polynomial 3, right? So this is a function. So you give x, if you plug in x value as is equal to 0, so this is like a box. F of x is a box which is going to take input value x, and in mathematics we have seen this, right? So where x, let's say x is equals to 1, so which is 1 cube plus 1 square plus 1, which is going to be 3. So the output of this function is basically 3. So when x is equals to 1, when x is equal to, what will be? So this is nothing but a function. In our case, we don't have x can take only 0 or 1. So the function is basically a combination of these inputs, which is f is equal to a plus b c bar. So that was the final answer I got. That is not that is a reduced expression. But what here I'm writing, we just put f means the final output. Okay, so then you can use the f function. Here f I use the simple figures for function. So mathematically we call function, right? So here we have 3 variables, and each of these variables can take either 0 or 1. Okay.
And you can do the same thing to define 0.
Yeah, that is called as, we will do that. That is called as product of some sort. This is sum of product of 0 also we can take. I have that notes actually. So we are looking what we are looking is we are looking the truth table, and seeing the combination of inputs for which the output is what. So that I'm expressing in sum of product form. Why it is called a sum of product form? Because these mean terms are in product form, and this is the OR gate, right? This is the sum. So this is the sum of product form, or they also called as canonical sum of product form. I don't know why mathematically they called as canonical sum of product forms. Canonical sum of products. I will explain that as well to you. Okay, I think I wrote this. Yeah, I have written, I think. So other way of writing the expression also, I think I wrote. Yes, I think I wrote. Okay. And this product of sum. This is sum of product. Remember that this is sum of product. We don't use normally product of sum, but it's better to know. But either you write a sum of product or product of sum. So this sum of product is directly we get it. Okay. So, but this is the expression I told you. So how to reduce this expression is A bar, BC bar, and here I can find AB bar as the common term, or what is common term here? Did I make any mistake? A, B, and sorry, here there's no C bar. I mean, I made a mistake. There's no C bar here, right? Because if I look onto this expression, which is for the output is 1. So this is A, B bar, and C, right? I made a mistake. I put a C bar here. That is not true, right? This should not be there. So I'll use eraser to eliminate this. You please watch. If I make mistakes, please correct me, because I'm not looking on the things properly. So please correct me. Okay. So don't assume that whatever I write is correct. So you follow my lectures. I can also make errors in calculation or errors in whatever. So this is A, B bar, C. So here I find that A, B bar is common. So C bar plus C. We know this is nothing but an OR gate. So plus C. So one is the inverted and one. You don't have to really know the law, but C bar plus C is going to be what the output is going to be 1, because one of the input is going to be this thing, right? And then what I how I reduce this, then I here I common term is AB and C bar plus C. So I will write this as 1. This is not 0. This is an OR. So this is 1, because one of the input is always going to be 1, right? So that's why we had an output of this one. So if you rewrite this expression, this is going to be AB bar plus AB. Again, we can rewrite this expression A, B, C bar. What I can do is I can take the A out and B bar plus B. Again, we know that B bar plus B is nothing but equals to 1. So we can this thing. So this is A bar, A, B, C bar. So a lot of students stop here. They don't use the, so can anyone, did you, so the final result is like, as I said, F is equals to A plus B C bar, but still we are missing something. Can you someone solve this further? Using some identity. I discussed this identity in the class. See, this lot of students think that this is the final circuit, we cannot reduce anymore, and let's solve it here, just stop it here. But you can, the final Boolean simplified expression is this one, which has 3 inputs of course A, B, and C, but it has one and 2 input AND gate, and 1 and 2 input OR gate. But here, if you see, this is a 3 input AND gate, right? Because we have 3 inputs to the AND gate. These are AND, right? AND form. And this is the OR form. So 3 input AND gate. So can you reduce this expression further? Think, did I ask you to do it? Did you do it? I mean, you can solve it. There are many ways to do it. If you want, you can try it. You can check whether what you're doing is right or wrong. Yeah. Sure. I have solved it different way, but I didn't use Demorgans law. But there are many ways to approach this simplification. Okay. I believe when calculators be used, just because it's do this. Oh, use this.
Okay, so this one, B, and C bar. That's good. I think using a able to using this away and then get A plus B C bar. I think get the substitute here. I believe
No, why did you cancel the A out?
I think I think do the Demorgans, I believe.
When you saw by the steps, was you don't understand directly knocking over A bar.
Um, due to let me see. Due to I think since this here. Oops. Since this is equal, since Demorgan's law, by using the same rule, you can knock out a bar from a b a bar b c and get a plus b c bar, I believe. I think I'm doing this correctly.
I think I'm getting what you moved A bar plus A okay. The identity, what identity used? So,
Demorgan's law?
that's not Demorgans law, is what identity I expressed in the last class. Demorgans law will have what we call it on from all forms, right? So it's not exactly Demorgans law, but I can understand what you wrote. So A bar plus AB, A bar plus AB. Actually, this is not okay. Thank you. Anyways, you can understand what you're trying to do here. But let me just
Erase that and I will rewrite. So I will erase this part. So this one, I can understand what he is trying, is making a mistake, but I actually is trying to approach in the right way, Sean. See, I explained a law. If you remember previous class, that was A plus complement of A bar B is nothing but is equals to what? R form, A plus B. We are going to use this law. So how we are going to use this law is actually in mathematics, we can always say that let X is equals to BC bar. So I'm replacing by single variable BC bar is equals to X. So which means that it is going to be A bar, right? And BC bar is nothing but X and plus A, which is nothing but A bar X plus A is, so this is of this form, right? So here it is, or you can write A bar B plus A. So using the commutative law, right? It's commutative, right? So it is going to be A plus B. So both are same. These both are same. So I have A bar X plus A is nothing but A plus B, which is nothing but, what is this going to be? Very good. A plus, it's A plus X. Yes, it's A plus X, right? A plus X. But then we can replace X with what? PC bar, right? So X with, but because we can now say that X is nothing but BC bar, because we said let X is equal to BC bar. So this is how I got the final answer. So there is a tendency to make mistakes here, because we will think that we cannot apply any further law. That's why I discussed these two laws, which is not given in the textbook, which is, I don't know the name of this. It's not a De Morgan's law. This A plus A bar B is one rule we got, one identity, like a trigonometry identity, we got one identity. So I don't know, the they didn't give any rule in that book. They just proved this. So I'm using this identity. Is that clear how I got it?
It says commutative law used.
I mean, this one, A bar plus B. I mean, I'm just switching here. So here, this A, I just wrote it like rewrote A bar plus A, because here it is in the form of A bar, this one for that. So that is commutative law, right? No, here, see, I'm talking about here, this one, A plus A bar B. What is that law? See, commutative law is in the R form is x plus y is equals to y plus x. That is the commutative law in the R form. X plus y, commutative law in the R form. So in the book, x plus y. Okay, you wrote that is an absorption law. Is that right? Okay, I got you why you wrote an absorption law. Let me see the absorption law. But that is not even absorption law. I don't know. What is your name? Jamie. Okay. Absorption law doesn't say that. Absorption law is like this. A plus Jamie, A plus AB is equals to A. This is the absorption law according to the, this is the absorption law. A plus AB is equal to A. This is the absorption law. A plus A bar B is equals to A or B. This is not the absorption law. Is that clear? Why I wrote commutative is that instead of A plus A bar B, I just say that A bar B plus A. So you can switch this, right? This X plus Y is equals to Y plus X. This is why, that's why I said it's commutative law, not for that point. Okay. For rewriting the second step here. So this is nothing but Y plus X, right? This is Y plus X. For this step, when I jump from this step to this step, I said that it is, I'm using commutative law. Okay. Because that is on the, it is like this expression is of the form. I just want to make a one-to-one analogy. But if your absorption law states that A plus AB is equals to A, that is the absorption law. This is the absorption law. Here it is not A plus AB, it is A plus A bar B. Is that right? So please understand that. Of course, you go ahead.
So which law did you use to get rid of big part?
See, that is the law, this one. This one I proved in the last class. A plus A bar B is equals to A plus B. You can verify it, showed with the truth table in the last class. So this law is not given in the textbook. That's what I was telling. This law, this identity. What law I was using is A plus complement of A with B is equals to A plus B. This is not given in the textbook. You can verify this is not given in the textbook. And this name of the law, I don't know, but this is I proved in the last class. A plus A bar B is equals to A plus B, which is nothing but OR gate, A OR with B. Is that clear? So this is this is not an absorption law. Absorption law is A plus AB is equals to A. This is the absorption law. You don't have to really know the law name, but for the initial stage you have to. But looking onto this identity itself, I can say if A and OR with A's complement and B, then I know that it is A plus B. You can prove it. Of course, this such kind of proof will be asked in the exams also, right? So these are equivalent expressions, right? So this is not absorption law, guys. I don't know. I mean, I will try to find the name of the law. This is not given in this, not in the textbook. So this one, it is not in the textbook. Remember that even if you wrap around the pages, you cannot find this law in the textbook. Okay, so it's not given in the textbook. So please to make a please kindly make a note of it. So see, the other way I can do this is basically the same thing. I want to say that you can also use different ways. So A, B, C bar. I'm writing the expression again, and A bar, B bar, and C bar, and A, B bar, and C, and plus A, B, C bar. I'm rewriting the whole expression. I want to show you a different way of approaching this problem. Even if you don't know that law, that's fine. But I want to tell you the different way of approaching this problem. So this one I also wrote in my notes. So this is not even given in the textbook also. Please take a note of it. So A bar, B, C bar. This is what is common. A bar, A, B bar is common, and C bar plus C. We know that this is nothing but 1. And here A, B is common term, and C bar plus C. And this is basically 1, and this is 1. We know that this is 1, and this is 1. So until this point, we are correct. So A bar, B, C bar plus A B bar plus AB. And here again, I can, this is the same steps as I said it with the previous case, like if this is B bar plus B, and this is going to be A bar, B bar, C bar plus A. I'm not going to use the identity let X is equals to whatever, let X is equal to B, C bar. So we are not using, so I think I made a mistake. Is that right? A bar, B bar, C bar, is this? Okay, I don't know where this, see, thank you for that. Okay, when I writing, I just wrote incorrectly. So people tend to make mistakes, including me during when I was doing undergrad studies. I always make mistakes like this and lose points. So A bar, B, C bar plus A and B bar plus B, and this is equals to 1, right? So we have A bar, B, C bar plus A. Then see, we can also reuse the term, which we eliminated. So we can, in Boolean expression, Boolean algebra, this is valid. I'm going to take this expression, draw here and put it back here. Because I eliminated that, I can reuse the same expression to, this is going to be A, only this term. I'm highlighting this in green color, only this term, right? So this one, I'm reusing this one. I'm reusing this one. This is valid operation, so don't think this is invalid. I'm reusing the same term. So here I have this one, right? Now what I can do is that so I can sorry, I can use black pen. So what I can do is that I can A bar B C bar plus A B C bar plus A. I'm just rearranging this term, so I'm putting this one. Okay, again, this is commutative law. I'm putting this, rearranging this and putting A at the end. Now, what is common between these two things? Can anyone tell me what is common? No, what term I can go? A, no, A and A bar, but what is common term outside? Go ahead. B C bar, right? B C bar, and inside it will be A bar plus A, right? And plus A is there. We know that A bar plus A is what? 1. So which is nothing but BC bar plus A. So this step is not even given in the textbook. I'm just telling that I can also reuse one of the terms from the expression and simplify it further. So this type of logic you have to strike in when you're writing exams about that. So you have to think about it. But for that reason, I don't use snap like I use much powerful method to learn my businesses. But you have any term which is there. Now, in the sum of product form, so for which output is 1, that's very important. For which out, these are the terms for which, these are for the main terms for which output is 1, right? So we can use any of the main terms again, reuse it and solve it.
What's in the original?
Exactly, that's why I said for the main term for which output is 1. These are called as the main terms. All these say the truth table, right? The row, each of the row in the truth table is called as a main term. So I'm saying that you can reuse any of the main term for which output is 1. Yeah, what? So see, technically what I'm writing, how I'm writing this expression. I'm writing this expression for which output is 1. I'm not carrying over what is output here. Right? Questions? See, what we are trying to achieve is that minimize the number of gate and minimize the number of inputs, basically variables. But here again we have 3 variables A, B, C, but at least we are minimizing the number of gates in this particular case. I mean, we are having 2 input gate instead of 3 input AND gate here. So we reduced basically went from 3 input AND gate by doing one step. I'm not saying that if you do for the exam, if you think you leave this step, maybe you lose like 0.25 like that points. You won't lose like entire points, right? See, don't think that I have to arrive at this step. Students can leave at this step. That doesn't mean that it is incorrect. I'm not going to give 0. I may take few points, like 0.25 like that. I will take 0.25 points to not have the more simplified version. That's it. Right? Anyway, exam is open book. Assignments are also open book. Of course, assignment take home exams is open book, so you can think about it and see what is the final answer. Of course, you can ask our tutor David also to verify your answer before you submit to me. Okay.
So then when we get to what we think is the most simplified one, go back to the function. Let's see.
See, other simple way I'm going to teach you the map method. With the map method, you will directly get the expression. You won't have problem. So for the explaining the Boolean, because this is using Boolean identity, I'm solving it. You can cross verify with the map method so that you have the reduced form or not to make sure, right? I'm going to teach the map method, which is Karna map. So I'm going to teach that. Okay. Any questions here, guys? You have a question? Okay. This is an interesting class. Okay. You know, this is not complex class. This is very interesting class. You see, the basic components that we build in the book, they have given 2-bit ALU. So 2-bit, what is the 2-bit ALU? Arithmetic and logical unit. So this is how it has been designed inside the computer. What is, if you go to page that looks like a complex circuit as such, but if you nailed it down, it is very simple circuit if you know. So this is how you're basically designing a CPU. Basically, inside the CPU, you're designing the arithmetic and logical unit. Let me just show you the page. A simple 2-bit ALU. So see this page. Simple 2-bit ALU we are having it. One something. So with whatever the knowledge we are gaining, so we are having that simplest circuit. Right? So this is you look onto the circuit, it looks complex, right? But as such, you know all the basics. It should be that right. Questions? Right? We'll see how the circuit is being constructed. See the bits and components. So we are going to approach the circuit by learning all this method to approach how we're going to get this circuit. There's no explanation given in the book, but I will give you a detailed explanation. Please watch. That's why I'm recording this video lecture as well, so that you can rewatch that. Because you are taking 5 courses, I can understand that you can forget easily. You know? And I'm teaching 5 courses also, it's very difficult. I'm teaching 5 courses this semester, but some sections are overlapping, that's fine. But still, it's easy to forget. So that's why I'm recording for your convenience as well. You can rewatch the lecture videos later. And if you find mistakes also, please let me know. If there is any mistake I'm making, please let me know. All right. Anyway, I hope I convinced you how I got this. So this is actually I never used a product sum of product form, but I want to explain for the sake of completion. I want to explain. I never used, even in my undergrad when I was doing this this thing. I never used I never used product of sum. I use only sum of product. But there is also product of sum, because someone raised the question. Now I had to teach what is product of sum. So I'm trying to see. So I'll rewrite the truth table for you guys. So okay. Actually, when you write, it is not this. You're looking at. So let me write this in this truth table again, because I don't want to erase that. So ABC. So this is for the expression f is equals to b plus c bar, right? I spend enough time on this chapter because I don't rush through this chapter, because I feel this is an interesting chapter. So how you can build a, if you know how to build a 2-bit ALU, arithmetic logical unit, you can definitely build a 4-bit or 8-bit, whatever. So it is going to be even more involve more gates and more number of connections, everything. But at least you'll appreciate this is not, we are not learning just for designing some fancy circuits, but actually we are trying to build a computer, right? With this course, I seriously feel this course should be not 141 level course, it should be 200 level course, because we are covering a lot of things in this class, to be honest. So but unfortunately is 141 here. So anyway, it should be 200 level course. Okay, go ahead. Oh, this one I wrote. This is the truth table, assuming that I give the truth table to you. Don't worry about it. Okay, I'm giving the truth table. And in the exam also there will be truth table. Or if you go to my assignment here, that you have to write the truth table based on reading. So here I say that I will give you another example. Okay, we'll go with another example as well. Just I want to explain this. But for this example, see the truth table, you have to figure the truth table. Design a circuit with 3 inputs X, Y, Z, representing the bits in binary number, and 3 outputs, 3 A, B, C, also representing bits in a binary number. When the input is 0, 1, 6, or 7, the binary output will be the complement of the input. When the binary input is 2, 3, 4, or 5, the output is left shifted with rotate. There is an example. Show a truth table, all computation for simplification of the final circuit. So this will be the statement that will be given in the exam or the assignment. So you are going to make the truth table by reading this, and then you are going to simplify that expression either using Boolean identity or Karnaugh map. We are going to talk, and then give me the final expression, and then design the final circuit. So here I'm giving you the answer directly, A plus B C bar, but actually we don't know, right? So it is not given upfront for you. So that's why when I explain more problem, you'll understand. But now, right now, I'm giving the truth table directly, so you don't have to worry about what is the truth table. But what is a product of some form? So again, we will write an expression like this: sum of product. So now these are the min terms: M0, M1. These are called min terms. M3, M4, M5. That's M means min term here, right? So what I'm going to do is that I'm going to see for which the output is 0. So for M0, the output is 0. Is that right? For M1, the output is 0. And M3, the output is 0. So I'm going to, still I will write the expression as sum of product from only, but here it's for the output 0. So which is going to be 3, for 3 values in the truth table, the output is 0, right? For 3 combination of input, the output value is 0. So I'm writing that expression A, B, C bar, and plus A bar, B, C. Do you agree with me what I wrote? Is there any mistakes? So this is for looking at the min term for which the output is 0. I'm looking on the combination of input for which the output value is 0. Any questions on it? How I wrote this expression? So this is exactly opposite of the other way. This is still not called as a product of sum. This is still, you know, looking at the min terms, and for 0 I'm writing it. I will derive, will go with the product term. So and what I can do is that I can okay, here we will write this is a complement function because it is f bar, because there it was producing output of 1, so f is equal to 1. Here I put f bar because I have seen the truth table for which the output is 0, so I don't put f is equals to differentiate from that I put in f bar, because for this combination of input the output is basically reverse, you know, it's opposite. Go ahead.
So let me, A bar, B bar, C.
A bar, B bar, C bar. This is for the first term, and this is A bar, B bar. Yes, thank you very much.
And I wrote this. See, I always make mistake. So, and he, I mean, this is even not clear. So, though this bar is not going over C. Okay, so I will just erase this bar too, or erase this whole expression. So, what I want to write is, so when you write the bar, also make sure that you place the bar exactly on the top of the variable. Don't extend to the next, because when you write it very fast, it looks then wrong, and I will also grade it as incorrect. So this is A, B bar, and then C. Thank you for catching this. Okay, so this is how we try. This is again sum of product from for which the output is 0. So that's why I put F complement. Now we can apply Demorgans law. So actually we are actually applying Demorgans law, or you are taking you know, you can I will say applying Demorgans law at both sides. Okay, or you can say this F bar bar. So I think this is applying Demorgan. So I'm putting F bar bar. So to negate that, and A bar, B bar, C bar plus A bar, B bar, C plus A bar, B, C. I'm writing the whole expression and putting the bar. I'm taking this bar on both sides. Right? Is that clear? So this circuit will produce output 0. But what will be this circuit will be producing? 1, right? I'm putting bar on the both sides. You know, F double bar is nothing but it's what is it called? Law called, like every time I forget this law, double complement law. So which is going to be F. But here there is a bar. So here I will write, again, I didn't, again, we are doing the Demorgans law only here. So what I'm going to write this as, so A bar and this bar will become single A, and this will become B, and this will become C. See, one thing, see, all this dot is nothing but AND gate. So all the AND gate will become OR gate here. So which is A plus B plus C, but this is having double bar, right? So then it is going to be all these bars will go away. And now we have this plus will become dot over here. Okay, this is the Demorgans law for 3. I will talk about this, but right now remember that. So this complement will go away, complement because B is already having a bar, right? So and there is another bar, so that will I actually using what is it called, double complement law. This plus will become dot. So this is actually applying the Demorgans theorem. So because A bar and then bar is there, so which will be A and then plus B. And what will be the next expression here? Plus, can anyone tell? It should be C bar. Very good. So this should be C bar, right? And now A is here. See, all this plus is becoming a dot here. So the plus means it is an OR gate that become an AND gate. And here A bar, this thing, though, that is going to become A and plus B. So what is going to be? It's B or B bar? B bar and plus C bar, right? So all this dot, see, this dot become plus here. See, all this dot will become, it will become opposite. Exactly. So this is actually the product. What we wrote here, it is not sum of product terms. So what we got here is the product of some firm, because we have product. So all these are products, right? So this is called as product of some term. See, I will give you this an exercise. When you solve this product of sum, what you are going to get, the final answer is F is equals to A plus BC bar. I will give you an exercise you can do at home. So I wrote the product of, did you get my point how I wrote the product of sum? So I look at the term for which the output is 0. So I put F bar and then I'm taking complement on both sides. It is actually applying Demorgans on both sides. F double complement becomes F, and this, all these things will change. So it's very easy to remember Demorgans law. So dot will become plus, and plus will become dot, and bar, A double bar will become like, because that is using that double complement law. And here I'm writing. So this is the product of some term. Okay, we generally don't go, but for the sake of explanation, I want to come, for the sake of completion, I want to write the product of some form. Product of sum. We generally don't go in this way to reduce the Boolean identity. We always use sum of product, like looking at the min term for which the output is 1. So this is called as the product of sum. Is that clear? So this is equivalent to this. They are basically same, but again you have to use Boolean algebra to reduce the circuit. Is that clear? And product of sum, again you can use Boolean identities to get the final value, which is A plus BC bar. I will leave you as a part that you can prove. You can do it once from home. And are you getting my point? So you can use sum of product or product of sum. Little bit lengthy you can do. General people use sum of product that we use for beta for this output is 1, and then do it. Generally, I don't use Boolean identity to reduce expression because we tend to make mistakes. Right? So I'll give you a few more examples now in this class. And please stop me because now one down for when this class is actually right. So now I will give three more examples, and then I will explain XOR. XOR, we see exclusive OR, right? We see what is the non-gate XOR. XOR is also very interesting. So the XOR gate says that A bar plus A bar B plus A B bar is equals to A XOR with B. We will see what is XOR. That is a odd detector. That's called as how it will detect the odd number of ones in the circuit. If there are odd number of ones in the input, odd number of combination of ones, then it is going to produce 1. If it is going to be a number of ones, it's going to produce 0. So that is the XOR. We'll talk about this, which is very, very important for building our adder circuit. We'll talk about XOR, but before that, for giving an example, I don't know where I have my other sheets of XOR now. Did I have it? This is again given. Okay, let me. I think I have time. Oh, where did I? Forgot that one. So we'll solve the Boolean expression a little bit, but let me just give you a simple circuit. I think, did I discuss this or not, right? Let me just go, because for the question that is asked by, I don't know your name. What is your name? Yeah. Tyler? Callis. Okay, Callis. So yes. So the question is like this. Consider a, I will give you a few example of, I will tell you a few examples in next class for, I didn't bring the sheet, I guess, but I have other things to cover. So consider a simple majority circuit. So this is an example I just want to give. So consider simple majority circuit. So this is how the problem statement is going to be, or a function. It's not circuit. And this is a function. This is a function that when given three inputs, outputs basically when it is given three inputs, outputs 0 if less than half of its or 1, and outputs 1 and outputs 1 if at least half of its input are inputs are 1, right? So this is a simple majority function. So basically what we are going to do is the truth table, right? So read as problem statement. So we have three inputs. They are given explicitly in the question. So let me just write that problem here. So I will use this board. So this part of the board. So x, y, z, and this is the output f. So we don't know what is the function basically. We know that the problem statement. So we have to write as again 0, 0, 0, 0, 0, 1. Don't always follow ascending order in binary numbers. Don't write in any other order. So it should be ascending order, otherwise you'll make a lot of mistakes. So this is an ascending order binary number, right? 101 and 110. So what is the problem is stating here? So this circuit is going to produce output of 1. So given three inputs, it's going to output a 0 if less than half of its are 1. So how many ones you can have is 3 ones. So less than half of its are ones basically. So so here how many ones are there? There is no 1. So what will be the output of this? 0. And how many ones are here? 1. This is not half of its 1, right? So again, the output is going to be 0. And here 0, 1, 0. Again, there is only 1, 1. So this is not half of its input or 1. So still it is going to output a value of 0. And here 0, 1, 1. So here we have 3. So this is how it is, like it says it outputs a 1 if its output is 0 and outputs are 1. So this is a statement. If half of its inputs are 1, so more than half of these inputs are 1. So here it's going to be 1, right? How about here? The output 0, and here 1, and here 1, and here also 1. So this is our truth table we got, right? Now we can write the sum of product form. Sum of product form. So this is a f is going to produce. So we are looking at the min term here. So M0, these are called as a min term. Each row in the truth table are called as a min term. And min term is basically the combination of inputs, using the AND gates that are called as a min term here. So these are the combination of inputs. Basically, we are ANDing it, all the inputs, right? So f will be, so we have to look at this M3 because it produces output 1. So that is going to be what? X bar. And because X is 0 and Y is 1 and Z is 1, it's going to produce an output of 1. And here, when X is 1, Y is 0, and Z is 1, the output is 1, right? And now, again, Here x is 1, y is 1, and z is 0. The output is going to be 1, right? And finally, it is going to be x, y, z are all output 1. So this is the resultant Boolean expression that you got. But again, as I said, this is not the complete circuit. So this is going to be what? This is going to be not a reduced form of the circuit. So you can use Boolean identity or you can use K-map. K-map, you don't have to write the sum of product form in this way. But for Boolean reduction using Boolean algebra, I'm using this. Again, you can reduce this circuit. I have not reduced the circuit in myself. So can someone come and reduce the circuit on the board? Who can use Boolean identity? I mean, I don't have an answer for this. To be honest, I just wrote the expression. I didn't have an answer. Someone can use the Boolean identity to reduce the circuit, will be good. Right? Think what we can take out. So I think we can take x, y, z bar, z, you can take here out, right? Is that clear? And here is there any common terms within this? This is x bar, y, z, y bar is there. Yeah, here, oh, here there is no common term. Is there any common term here? So, y, z. I actually, let me just, I don't find, is there any common term here? So this is not common term. So this will go away. So we will rewrite this expression, which is x bar y z plus xy bar z plus xy. But xy is also not common. How you reduce this circuit further? Okay. You can take z out, and this is x bar y and x y bar plus xy. Am I writing? If I'm making any mistakes, let me know. See, that's why you always use K-map, because for me, I don't remember the Boolean identities. I use K-map to reduce the circuit. But I find a pattern over here that is different. But I didn't teach you that. But can you reduce the circuit? Can anyone come and help me to reduce the circuit? I mean, this one was easy to do, but this one, I don't know how to combine. And xy is there. What is common? Oh, okay, I can do this, right? No, I cannot do that. xy, x, y. Anyone can do it using identity, some identity apply and reduce. But for me, I can remember this identity for sure. This is nothing but x XOR with y xy. So because I didn't teach it, XOR. As I said, there are different circuits within the same, so you don't have to worry. But here I use this one. But anyway, leave the point to you. So I didn't teach this. So don't worry about this. How I jump from here to here, I didn't teach you. I will tell you how to do. But this is one way of, as I said, Boolean expression can be like what? Can be many, right? Any questions? But I will leave the point. I don't want to write. I will erase this basically. I will leave this point until this point, because until you can reduce this for circuit for sure, but you have to use the appropriate Boolean identity to reduce the circuit from this point. Actually, I am stuck up here because as I said, I never use Boolean identity to reduce my circuit. I always use K-map for sure, because K-map for sure guarantee that I will get the reduced Boolean expression. But here you have to apply the right identity at the right time, and you should know think what identity can apply. If you have an answer, you can come and write on the board now. If you don't have an answer, I will give as an assignment. I can tell you the answer by using K-map easily. I can draw the K-map and I can get you the final expression. Cross check my answers. I mean, I don't want to do K-map now. If I do the K-map, I'll get the correct form, reduced form of the expression. You want to solve? Okay, so I will leave this as a take-home part or assignment. Think about it. I will also think about it because I'm not good in using identity. I'm good only with K-map. So K-map is the one I use. So you can reduce this expression still further. I think so. This is not the final form. This again, you can reduce this expression further, and you can think about it.
Again, I introduce product of some form. So product of the form is going to look at the meters for which the output is 0, and then you're going to say.
So let me just write the product of some form for this table. So f bar. So you have to write f bar. So for which the output is 0. This is going to be long expression. So I'm going to copy from my whatever I have written in my notes. So this is for which the output is 0. If there are any mistakes, please point me out. So these are the min terms for which the output is 0. So this is f complement, right? So there are 4 terms, 1, 2, 3, 4. So there are 4 terms for which, for 4 combination of input for which the output is 0. Is that right? So now this is again, and it's not in product of some form. So we will take complement on both sides, applying Demorgan's law. So this will be the whole thing here. So x bar, y bar, z bar plus x bar, y bar, z plus x bar, y, z bar plus x, y bar, z bar. So I'm taking complement. So this I can write x plus y plus z dot x plus y plus z bar dot x plus y bar plus z plus x bar y. So sorry, there is no plus here. This is dot, right? The plus will become dot over here, right? So x bar plus y plus z bar. So not z bar, z. So this is actually the product of some form. So this was a sum of product. This is the product of some form.
Right? Both are equivalent expressions. Both are equivalent. Again, you can reduce this and get a final form. I leave this as a assignment for you. So because I did solve, otherwise I'll go home and solve now. Because I can use enough to solve it. But anyway, I hope you got the point there. Even I have questions. How I use some more product. Anyway, let us. I have some more notes on Demorgans. I still have
15 more minutes for this class. So let me just rewind the Demorgan's law. So as I said, Demorgan's law, you can write like this: x, y, the whole thing, prime, x prime, y prime. This is the notation that they used in the book. But if you are going to use bar, please use bar, which is going to be this whole bar is belonging to x and y, not individual separate bars. Then it is going to become separate bar, x bar plus y bar. So this is going to be the Demorgan's law. And this is the, what is this, the and form. For the or form, the Demorgan's law like this. So this is x plus y, the whole thing. This is the prime. This is x prime and y prime. Or x plus y bar is equal to is nothing but x bar y bar. One is an OR gate, one is the NAND gate. We discussed this one last class. So this is a Demorgan's law, right? So now I just want to prove that what I want to prove. So I have a function which is taking 3 inputs, f, x, y, z. So function which is taking 3 inputs, and it is going to result in output of x plus y plus z. And complement form of this will look like f bar x, y, z is going to be, this is the complement form, right? I'm using the bar form. I'm not using the prime. So this is bar. So this is the whole thing, right? So this is the complement thing. Let me rewind. So what I wrote is, so see x, this is x plus y plus z. This is f complement. I hope you got this point. And so this is can we apply the Demorgan's law, because the Demorgan's law is stating here is that this is the Demorgan's law in the R form, right? But this is for the 2 variables. Is it given for 2 variables, right? Can we extend to 3 variables the Demorgan's law? Yes, you can extend. That's what we reduce in the product of some form. Basically, what this will boil down to is, when you take a Demorgan's law, so this is going to be boiling down to x bar, y bar dot z bar, which is what I can prove this again. So how I will prove is basically let w is equals to x plus y, and so f complement will be then x, y, z will simplify to w plus z bar, and which is nothing but R form is W bar dot Z bar, right? And then we know that what is W bar is nothing but, we read W is equal to X plus Y, which is nothing but X plus Y, the whole bar dot Z bar. Again, we can use the Demorgans law and say it is X bar, Y bar, and Z bar. This is how I got directly root. So I just proved it here, how I can extend the Demorgans law to more than 2 variables. Any questions? So Demorgans law is stating for 2 variables, right? This is in the R form. But what I did is that, this is the original function. I'm taking the inverse of the function, which is going to be bar. So always you can take inverse on both sides. So then we can apply Demorgan's law, because this will produce output 1, means F complement will produce output 0. So that is the difference here. But are you able to understand my point? How can I extend my Demorgan's law to more than 2 variables? Right. So this is given, this proof is given in the textbook. And this function is called as the inverse function. When I say this is, you see, this function is f of, here looking onto this function, I don't think we can simplify, but when you say the De Morgan's law applies, so we have what is called f bar. F bar is nothing but is equals to, we got from our here, so I will copy from here, so which is going to be here, right? So f bar x y, this is nothing but inverse and inverse function. For every Boolean function, we can have an inverse function. That's what they mean in the textbook. Like if there is a circuit that is going to produce output value of 1, then we can have a complement form of the circuit which will produce the output value of 0. So that's what the complement. So this is called inverse function. So this is the actual function, right? This is the inverse function. Inverse function is looking like this. Any questions here? This is given in the textbook. This I took from the textbook only. Any questions? I don't know if I'm teaching a lot of mathematics or just normal. This is easy mathematics, right? You think it's difficult? It's not difficult. Right? Easy mathematics. Okay, this also I could take an example from the textbook. I'm going to do this. You can also watch. So there is a function which is going to take 3 inputs, x, y, z, similar to what, f of x. Here there is a function which is taking mathematics, x cube plus, this function is having x cube plus x square plus 4. This is a polynomial of degree 3 function, right? So this is f of x. So similarly, we have a function x, y, z. Here we are having 3 inputs, and which is going to result in the output of x bar plus y, z bar. So this is my function. So this is my function. Given a function like this, given a function, what will be my inverse function? What will be my inverse function? You put f bar x, y, z. Again, it's going to take the 3 inputs. So we don't put a bar here. We just put on the top of f, right? Is this, looking like f or not? So this is f bar. This is my complement form, right? Complement form. So what will be the here? Then we can have to take complement on the whole thing. Is that right? This will be my inverse function. But this function looks complex. And what we can do? So this one we can write again. Let me see how I wrote it. I myself didn't write. So this is going to be applying De Morgan's law both sides. It is going to be x double bar, that is going to become bar, and this is going to become plus, is going to become dot, and y is going to become y bar, and this is going to become z. So this is like similar to what I wrote in the product of some form, right? So very easy. So taking bar, so plus will going to become dot, and here there's a dot that is going to become plus, and this double complement, it will cancel out, it will become x, and here this complement y bar, and this is z, double complement is going to be z. So this is my inverse function. In the exam, if you're asked to find inverse function, don't stop here putting a bar. Try to give in this applying Demorgans law. So this will be the final function. Of course, this function is correct, but this is cryptic, actually very difficult, you know. But here I just use Demorgans law. So this is my final value of this function. See, let us verify this function. I still have time. Okay, I'll just verify very quickly. So this is a complement function indeed. Indeed, these are both are same. So not same. So if this function is producing output of 1, the other function will produce an output of 0. Let me just prove that quickly. I wrote in my this thing. So with that, I will complete the class. So we have, of course, x. See, for this all we need x, y, z. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Please try to align and write. Otherwise, it will be difficult to look and write. 1, 1, 0 and 1, 1, 1. Right? Now we can write x bar, y bar, z bar because I need that. So x bar, y bar, z bar. So that is exactly opposite of this. What is the value of x? Inverter, right? This is going to be 1. 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 This is all going to be 0. And y bar is basically this is going to be 1 over here, and this is going to be 1, and 1 is going to become 0, and 1 is going to become 0, and 0 will become 1, and 1, and 0, and 0. And z bar is actually is going to be 1 here and 0. I'm looking onto the z value here and inverting that. And 1, 0, 1, 0, 1, 0. I hope I wrote everything correctly here. I don't think I made a mistake. So 1, 0, 1, 0, 1, 0, 1, 0. So I invert. So for first thing I want to know is that I will write the function here again on the left hand side. So what I was having as function is basically I'll write on the top f of x by z was like this, right? Which is x bar plus yz bar, and complement form of that will look like xyz, which is nothing but x dot y bar plus z, right? So this is the complement form of that function. So let me do the x bar. Now we have to combine this, right? So now first we'll combine these two, because these two columns, because y bar z we want, because sorry, we will combine this, not y bar. We will combine this one with this, right? Try to understand what I'm doing. Otherwise, I can explain next class if I'm running out of time. So this is going to be y z bar, right? So y z bar. So this is an AND form. So I'm looking onto this value and writing. Basically, this is going to be 0, and this is going to be 0 again, and this is going to be 1 because 2, and this is going to be 0, and this is going to be 0, and this is going to be 0, and this is going to be. I hope I'm writing it correctly, and this is 0. Let me check my this thing as I wrote correctly. Yes, this is fine. Then yz bar. Then we want to find x bar, y bar, z, because this is for the f, right? F is given there like that. So for that we have to combine this with this. So we have to look onto this column and then this column. I'm putting a tick mark, or maybe different colors. I think this I got from the textbook only. So I put a tick mark. I have to look, and this is an OR, right? OR gate. We are ORing it. So what I will write is basically here it is going to be what? Tell me, this output is going to be what, Sean? 1 and 1 OR with 0 is what? 1, and 1 OR with 0 is 1, and 1 OR with 1, and 1 OR with 0 is 1. 0 OR with 0 is 0. 0 OR with 0 is 0. 0 OR with 1. You have to look at the right column. So 1, and 0 OR with 0 is 0. So this is the output of the function, which is basically this is the function where I'm getting the output. This is the not the complement form. This is the output of the function. I will leave you exercise because I'm running out of time, I think, or I don't want to go fast. But here you have to take y bar plus c. So if you want, I can write quickly. I don't know. So I just want to prove that these are indeed complement functions, right? So I think I have still 2 more minutes, or we can do in the next class. I just want to prove that these are complement function. What this is producing 1 means the other circuit will produce 0. If this circuit is producing 0 means the other circuit will producing 1. If this is 1, then that will be 0. So I will write that one. I will leave this step. I will continue with the next class. All right. Or you can do it and verify that what I wrote is indeed a complement function. Right? I'll leave it as exercise. Please let me know next class. All right. Thank you, guys.